Great. So we're going to take a look at what you got when you put these values into Excel and created a chart. Now, the linear trend line, if you didn't set the y-intercept to 0, came out with an r-squared value of 0.95057. So that means that the correlation coefficient would be the square root of that number. And the square root of 0.95057 is approximately equal to 0.975. So that looks like a pretty good correlation coefficient, but remember that the problem was that at time 0, we expect that the object has not fallen at all. So in this situation, we wanted to set the y-intercept to 0 because at time 0, when the object is released, the distance should be 0. So when we do that, we end up with an r-squared value of, this is the correlation, the coefficient of determination is 0.84904 is what was returned to us on using the trend line. If we take the square root of that, it comes out to be approximately 0.9214. And that looks like a pretty good correlation coefficient until you start to take a look at the data. And here, this is the one for the where it's set to 0, and what I've got down here is for the when it's not set to 0, but both are approximately the same. The line of best fit is a good model because the r-squared value is high and the r value is high. So the correlation coefficient and the coefficient of determination are quite high. So it seems like that's a pretty good data fit. But it's a poor model because the trend of the points definitely shows a curve here. So we don't want to use a linear trend line. Also, the y-intercept should be 0, which really reduces the correlation coefficient. Now, when we change the trend line to a power, the equation you should have got was y equals 4.7803x to the power of 1.9876, so pretty much close to a quadratic, which, because remember, a quadratic is x, could be x to the power 2 is an example of a quadratic. And the correlation coefficient here is going to be the square root of the coefficient of determination. So in this case, this works out to be approximately 0.9997, which is very close to 1. So it's very close to all the points falling on that particular curve. And if you sub into a calculator, so we've got when we sub into the equation, we're subbing in for x equals 2. So we do 2 to the power of 1.9876. And if you don't have a scientific calculator, you have to do that operation first to put it in brackets and then multiply by 4.7803. And you should get an answer of approximately 18.96. So that means that after 2 seconds, the object will have fallen about 19 meters. Now, if you put in second order polynomial for the trend line, you should have got an equation of 4.8485 x squared minus 0.0152x, and the r squared value, the coefficient of determination, was 0.99967. So that means that the correlation coefficient, or the square root of that number, is 0.9998. So that's even a little bit better of a fit than the power coefficient. Now, sorry, the power trend line. So next, asked you to sub into this. So when you sub in for x equals 2, you should get approximately equal to 19.36 meters. So that means after 2 seconds, the object will have fallen a little bit more than 19 meters. Now, when you change the trend line to an exponential trend line, then you end up with coefficient of determination of 0.91605, which translates into, when you take the square root of that, you get a correlation coefficient of 0.957, which appears pretty good. But the problem is when we sub into the equation for y equals 0.0683 e to the power of 4.9978 times 2 is our x value. So I'm going to call up the calculator just so that you know how to do this calculation if you ever are trying to decide if you're dealing with a logarithmic trend line. So it's 4.9978 times 2 e to the x times, and in this case, it'll be 0.0683, and you get approximately 1,497. And this will be meters, which is pretty close to 1.5 kilometers. And if you're following 1.5 kilometers in 2 seconds, there's no way you will ever parachute. So we can automatically throw out this particular trend line. This one obviously doesn't make sense. So if you're trying to decide based on an experiment which trend line you should take, then you're either going to pick the second order polynomial, or you're going to take the power, because they came out with pretty close results. And the only way that you could test this is in an experimental situation, you would have to repeat the experiment, see how far the object fell in 2 seconds, and calculate using your model which one best fit the data. Or in the case of taking surveys or looking at data itself, then seeing how good of a predictor your particular equation is to match data that you find later on, or to extrapolate or to interpolate.